Hi, this is David Harper of Bionic Turtle. I'd like to briefly draw the difference between duration and the key rate shift technique. In tomorrow's movie, I'll show you how to calculate the key rate. Here, just to illustrate, I've imagined a term structure of interest rates. So this is the familiar yield curve for spot rates, and what that means is that each term, for example at the 3-year term, there's a corresponding spot rate, in this case about 4%. The most popular measure of bond sensitivity is duration. Duration is the D in this formula here. So here's the formula, and if we have a duration, what this tells us is if we assume a shock or change to the yield, say a 1% change in the yield, multiplied by duration, that returns or give back to us the percentage change in the bond. There's a negative here because an increase in the yield will correspond to a decrease in the price of the bond. If I multiply both sides here by the price of the bond, then I have this formula here, and what I have is given a duration and the price of a bond, then I can shock the yield or change the yield, and this here gives me an estimate of the change in the price of the bond. That's why duration is an important risk metric, because it's telling us about the sensitivity of the price to changes in yield, the underlying factor. However, it's a single factor model, so this is its limitation. Technically it's a first order partial derivative, but it's a single factor model, and the reason we use it and like it is that it's very convenient to be able to summarize the single underlying risk factor in duration. However, we know at the same time that's not realistic. If we look at the term structure of interest rates, what we're assuming with duration is that it's changing in parallel, because we only got a single factor. We can't get more complicated than that. So for example, if we shock the yield up, then duration is assuming a parallel shift in the yield curve. So you can see convenient, simplistic, and at the same time certainly not realistic. The key rate shift technique, in contrast, allows us to specify several factors. So we first specify a number of key rates. So for example, I may select the 1-year term as a key rate, and the 3-year term as a key rate, and the 5-year term as a key rate. And so now I'm going to shock with the key rate technique. I'm going to shock each of the key rates, and this will improve on duration because I've really allowed myself to estimate the impact on the bond with multiple factors or multiple key rates. And I can still collectively, if I shock all of these rates up by say 1%, then the collective vector of key rate changes will approximate that parallel shift of 1%. So what I have with the key rate shift technique here is the shift in the term structure is a function of a vector or a set of not one parallel shift, as is the case with duration, but instead a vector of key rate shifts. The change in yield here at my first key rate, so that may be the 1-year mark, the 1-year term. My change in yield or shock to the yield at the next key rate, which may be the 3-year term, and so on. So I can select the number of key rates, and that typically may be from 5 to 11 along the yield curve. And what I get is I get more realism, improved realism on the duration, which was that single factor parallel shift, at only the cost of some incremental complexity because I've now added several factors. But the important thing is I can start to model a shift in the yield curve that's more realistic, that may not be parallel. So that's the concept of the key rate shift technique, and then the next tutorial I'll show you how we calculate it. This is David Harper, the Bionic Turtle. Thanks for your time.